Welcome to the lecture 12 of the course Transportation Network Analysis. So, in the last class we had just started to discuss about seeing and solution algorithm for solving the traveling salesman problem. So, just to recall, since the traveling salesman problem is NP hard, so it is not possible to solve it optimally in polynomial time. So, therefore, we are looking forward to an approximation algorithm as can solve this problem approximately, but in efficient time or in polynomial time. Okay. So, before we present this main algorithm here, we will be looking at a smaller algorithm that will be used in that main algorithm. So, that smaller algorithm is this. So, this algorithm finds the pre-order walk of a tree. Okay, this is a recursive algorithm. So, as you can guess here, so the input of this algorithm should be a tree. So, this is this algorithm here. So, this algorithm takes the input a tree. The first thing it does is that it visits the root node of that tree and then it traverses the left subtree of that original tree, and there it calls this pre-order function, but now the input to that function is the left subtree. Okay. So, and that is why this is a recursive algorithm, because in this step it is again calling back this main function, but here now the input is the left subtree, and after that it will traverse the right subtree and again it will call the pre-order function, but now the input to this will be the right subtree. Let us take a look at this through an example here. So, on the right side we have this tree given to us. Okay. So, the first step is that we visit the root node. This node A is the root node here. Okay. So, you can see that the first node that gets listed here is node A here. Okay. After that we traverse the left subtree here. Okay. That is, we called the pre-order function, but with the left subtree. Now, this is the left subtree here. So, in that we will again visit the root node, which is the node B, and therefore, we have this node B listed here. Now, again when we will be calling this pre-order function, it will again visit the left subtree of this portion here, which is this node D here. So, therefore, we get this node D. Okay. And after that we will be visiting the right subtree here of this tree that had B, D and E, and after that we will be coming out of this subtree and then we will be going to this subtree which consists of node C, F and G, and there the root node is node C. So, therefore, we have this here, and again it will call the left subtree here, and therefore, we will go to node F and then finally node G. Okay. So, you can see here that we first visited node A, then B, then D, E, C, F and G, and that is the order in which this is written. So, this is a pre-order walk of this tree. So, in order to implement this algorithm, we need an input as a tree and the output that comes out is the pre-order walk here. Okay. So, now we will be presenting the main algorithm for this traveling salesman problem. So, the way it goes is that let a node be a origin node. Okay. So, let A be the origin node where we want to start the traveling salesman tour, and we construct a minimum spanning tree using Prim's algorithm by initializing node A as the starting node. So, if you recall, in Prim's algorithm we started with an arbitrary node here. So, just do a modification that instead of an arbitrary node, let us suppose that we have some origin node specified in the beginning here. This origin node can in fact be any node of this graph. Okay. So, we construct a minimum spanning tree using Prim's algorithm. So, since this minimum spanning tree will give a tree, so there we will visit the nodes in the tree in this order through the pre-order walk. Okay. Where we will be considering this origin A as the root node. Okay. And then we will make a tour using this above list that we get. So, we will get a pre-order walk from this second step, and from there we will be just adding this node A or the origin node at the end, and that will be giving us a tour. Okay. In order to understand this, let us take a look at an example here. So, this example has been taken from this book by Corman and others on Introduction to Algorithms. This is an example of a complete undirected graph. Undirected, we have defined before that a graph where the edges do not have directions, and a complete graph means that every pair of nodes has an edge connected to it. Okay. So here you will see that every pair of nodes has an edge connected to it. For example, from D to E, this is that edge. From E to G, this is that edge here. Now the edge between D to E, since it will be overlapping the one which is going from D to E and then E to G, so that's why that edge has been showed in a curved way. Although the length of this edge DG is the sum of the edge length of DE plus EG. Okay. So the length of these edges or the weights of these edges is equal to these distances which are shown in this Cartesian plane here. Okay. So this is a complete undirected graph, that is a graph where the edges do not have directions and every pair of nodes is connected by an edge. Okay. Now on this graph, the first thing that we do is that we construct a minimum spanning tree using Prim's algorithm by initializing node A as the starting node. So we implement this minimum spanning tree here. So let us suppose that in the Prim's algorithm we had first selected node A here. Okay. So now since this is a complete graph, so node A is connected to all the remaining 7 nodes that are shown here. So we will be adding that edge which has the least weight here. Okay. Now there are 2 candidates for that, one is this edge AB and the other is edge AD. Okay. Without loss of generality, we can add suppose edge AB. Okay. So we do that. Now currently we are having this tree which has nodes A and B. Then we will be again looking at that edge to add, so that we get a new node connected to the existing tree and that has the least weight. So you will find that node C is the closest to this tree which is consisting of currently A and B here. So we will be adding that and so on. So when we will be implementing this Prim's algorithm fully, you will be getting this minimum spanning tree here which is shown. Okay. Now since minimum spanning tree is also a tree, so we can implement the pre-order walk on this. So we set the root node here as the origin node. So we start from node A and then we will be going to the left subtree which is this one. So there also we will be first visiting the root node, so this node B. Then we will be going to node C, then node H, then node D here, then node E, F and G. Okay. So in this way we have obtained the pre-order walk on MST. So this figure here now uses the tour by using this pre-order walk here. So from A we had gone to B in the pre-order walk, then to C here, then to H, then H gets connected to D, then D to E, E to F, F to G, and then last thing that we do is that since it's a tour, that is it is a complete cycle. So we connect the last node in the pre-order walk to the starting node A here. Okay. So this is the tour that has been obtained here. Okay. So you can see that all of these nodes are part of this tour here and one node exactly once here. Okay. So assuming that the triangle inequality holds, so we had mentioned that this result rests on the fact that the triangle inequality holds. Given that this algorithm which we showed in the last slide provides a tour whose length is at most twice the length of an optimal tour for all the instances of the problem. So this result is saying that this algorithm which I just showed in the previous slide will always give you a tour whose length is at most twice the length of an optimal tour. Okay. And this will be happening for all the instances of the problem. So any example problem that you give, this result will hold. Of course, there is a proof behind this result, but we are not discussing it for the sake of time here. But this proof is available in some standard books related to algorithms such as the Corman one, which reference I had shown in the previous slides. Okay. So to see an example for this, so this was the approximate tour that we had obtained for the example shown in the previous slide. The length of this approximate tour is 19.1 units. How do you calculate that? Just add the lengths of all of these edges. For example, this is 2 units, this one will be square root 2, and so on. So you keep adding all of these edges, so you'll be getting 19.1 units. And we also know what is the optimal tour for this example. So the length of this optimal tour is 14.7 units. Now someone will ask, how do you get the optimal tour? Since this is a small problem relatively, it does not have that many number of nodes. So there are multiple ways you can find out the optimal tour. One way is that you list down all of the tours that are possible and then find the one which is having the least length. The other option is that we had also formulated this traveling salesman problem as an optimization problem. So you can solve that optimization problem using any of the existing solvers, and then also you can find that. Okay, but neither of these approaches, like either listing down all the solutions of the traveling salesman problem and finding the optimal, or using the optimization solver to find the solution of the traveling salesman problem, will be efficient if the number of nodes is very large. We will be finding that as the number of nodes increase, this will eventually become computationally very inefficient. So you can see that the length of the tour that you obtained here was divided by the length of the optimal tour. This ratio is less than 2 here, and therefore it is satisfying this result here. Okay. So therefore, if triangle inequality holds, if someone uses this algorithm, then if x is the optimal value, that is the length of the optimal tour, then through this algorithm we will never be getting the length of a tour exceeding 2x. Okay, that is what it means. Now when the triangle inequality does not hold, it is unlikely to find a polynomial time algorithm that finds an approximate value within a constant factor of the optimal value for all the instances of the problem. Okay. So let us see what does this algorithm mean. First, why it is saying it is unlikely, because this unlikely thing is based on the conjecture that there are these complexity classes which we have not discussed in this course, but there is a complexity class called P, and then there is a complexity class called NP, and there is this conjecture that P is not equal to NP, and assuming that that is true, this result based on that. Okay, although no one has proved that classes P and NP are not the same, but most of the people believe that probably P and NP are not the same classes. So therefore, if that is true, that P is not equal to the class NP, then when the triangle inequality does not hold, it is not possible to find a polynomial time algorithm that will approximate this optimization problem within a constant factor of the optimal value for all the instances of the problem. So what this result is saying here is that for the cases when the triangle inequality does not hold, so there is no such algorithm that can tell you that if your optimal value is say x, then you will be having an algorithm that gives you the value at most kx, where k is a constant. Okay. So that k being a constant, that will not be possible. Okay. For example, there might be some algorithms which might say that the value that this algorithm finds is say the optimal value, say x times some function fn, where n is the size of the problem. Okay. So then, since this factor fn is not a constant, it depends upon the size of the problem. So therefore, it may happen that, for example, if there are two problems, one where the number of nodes is say 2, n equal to 2, and the other is n equal to 10. So in that cases, the guarantee between the optimal solution and the solution we get from this algorithm will be different. So for example, if this n is equal to 2 and this function fn is exactly equal to n, that is, we have an algorithm which gives a guarantee that the solution that you get from this algorithm will give you a value which is at most nx, okay, where n is the number of nodes and x is the optimal value. Okay. So if n is 2, that is the number of nodes in the problem is just 2, then this algorithm will just give you a value which is just at most twice the optimal value. Whereas if n is say 10, then the guarantee will increase to 10x. So therefore, there is no constant guarantee for all the sizes of the problem. Okay. So that is what it is saying, that if the triangle inequality does not hold, there is not a possibility that we will be having a constant factor polynomial time algorithm. Okay. And whenever we say a constant factor polynomial time algorithm, that should be able to guarantee that it will give a solution which is having constant times the value for all the instances of the problem. Okay. But even though, if for example, if the triangle inequality does not hold and someone uses this algorithm that we just showed, where we are using the Prim's algorithm to find the minimum spanning tree, and then we are using this pre-order walk, this algorithm can still be used, because even though it may not give a guarantee that the obtained value will be within a factor of the optimal value, but in practice, for most of the examples, it might give a value which is close to the optimal. Okay. So such kind of algorithms where we do not have such a guarantee, they are called heuristics. Okay. So this is the terminology that we will be using. So if we do not have any guarantee on the performance of such algorithms, they are referred to as heuristics. Now, even though these heuristics do not have guarantee on the performance, they may perform reasonably well for most of the instances of the problem. Okay. Just that they may be not doing that well for some pathological or rare cases of different problems. So, just to summarize, we have now kind of categorized optimization problems with varying hardness. For example, the problems that are the easiest ones are the ones which can be optimally solved in polynomial time. This is important, okay? Like the shortest path problem, minimum spanning tree problem, and so on. For example, the shortest path problem, we had introduced this Dijkstra's algorithm, which is a polynomial time algorithm, and it is guaranteed to give you the optimal solution for all the instances of the problem, that is all the examples of the problem. Similarly, for the minimum spanning tree problem, we had introduced the Kruskal's algorithm and Prim's algorithm. Both of them are guaranteed to give you the optimal solution for all the instances of the problem, okay? And those algorithms are also polynomial time, okay? Then there are some problems that can be approximated within a constant factor of the optimal value in polynomial time, like the traveling salesman problem with the triangle inequality, okay? So for these problems, although it is not possible to find the optimal solution within polynomial time, but one can find approximate solution in polynomial time, and there is a guarantee that to that approximation. That is, example that we showed, the value that is obtained is guaranteed to be within twice the value of the optimal value, okay? And then there is this third category of problem, which are the hardest among the above two categories, is that these problems cannot be approximated within a constant factor of the optimal value in polynomial time, like the traveling salesman problem without the triangle inequality, okay? So for these problems, it is not possible to come up with approximation algorithms, but still it does not mean that we will not be solving these problems. Even though mathematical guarantees may not be available for solving these problems, but there might be some heuristic algorithms that might work well in practice, okay? So they might give you reasonable solutions for most of the example problems, okay? And therefore for those kind of problems, focusing on heuristic algorithms is important. So since we have these kind of problems, such as the traveling salesman problem, where the triangle inequality may not hold, so for those kind of cases, there are some other algorithms such as local search algorithms for solving the TSP problem. So this local search algorithm goes like this: it constructs a feasible tour, that is a route that visits each node exactly once and returns to the starting node through the set of nodes V. So suppose we construct this feasible tour where we have n nodes, so it is going from I1 till In, okay? So in this local search algorithms, we have this procedure of an L exchange, which replaces L links currently in the tour by L new links, so that the result is again a feasible tour, okay? So we will be looking at an example to understand this. For instance, two exchange procedure can replace the edges IU1 and IU2 and IV1 and IV2 with IU1 IV1 and IU2 IV2, okay, to obtain this new tour. So here you will see that it was previously IU1 IU2, but now it is IU1 and IV1. Similarly here it was IV1 and IV2 before, but now it is IU2 IV2 now, okay? Let us take a look at this through an example here. Suppose we have this graph here, okay, on the left. So we currently have a tour here which is going from A to B, then B to D, then D to C, then C to A here, okay? So suppose we want to do a two exchange procedure here. So suppose let this IU1 node be node C here, IU2 node be node A here, IU1 node be node B here, and IV2 node be node D here. Okay. So currently A and C are connected to each other and B and D are connected to each other. So we'll do a swap here. So we'll now connect A to D and B to C here. Okay. So now this is an example of a two exchange here. Okay. So this is what we finally get if we do a two exchange here. So instead of AC and BD, we have now replaced with AD and BC. Okay. So we'll be continuing this discussion on local search algorithms in the next lecture. Thank you.